Anybody deployed IPv6? Great. So you know all this already, and I don't need to do this talk. Fantastic. Now then. Let's see. So I'm David Holder. I'm delighted to be here. Thanks for inviting me, and thanks too for Erion for funding me attending this event. What I want to do is give you a very quick overview of IPv6 security, particularly focusing on the threats and the vulnerabilities to give you an idea of what's out there, but also to go over the main IPv6 security features that you can use to address some of these threats. But before we do that, let's have a quick look at some common misconceptions. There are two big mistakes that people make with IPv6 security. The first is that IPv6 is more secure than IPv4, and the second is that it's less secure than IPv4. And both of these are wrong. And the reason that they're wrong is there's an underlying assumption that people are making. And that is that it's meaningful to compare IPv4 security with IPv6. But it isn't. And the reason that it isn't is that the IPv4 networks that you have, those who didn't put up your hands, they are in fact IPv6 networks where you're using the legacy support for IPv4 that's in the dual stacks on the platforms in those networks. Because today, all the major operating systems and almost all of the equipment that you're using is actually built upon IPv6 and IPv6 dual stacks. So most of the vulnerabilities that we're going to talk about are actually there already in your supposedly IPv4 network. So ideally, you should have secured your network for IPv6 vulnerabilities maybe a decade and a half ago. There is another big problem, and David had this on one of his slides: training and education. One of the biggest security risks that you will face is the fact that people underestimate the size of the differences between IPv4 and IPv6. The big assumption is that IPv6 is just simply IPv4 with longer addresses. But it isn't. There's an awful lot more, as we'll see. Even addresses are massively different in IPv6. They're different beasties. They have different attributes. They're used in different ways. So, let's have a look at the threats and vulnerabilities. Here's my meaningless slide. You should never compare IPv4 with IPv6 security, so let's do it. And the reason I'm doing this is to give you an idea of the scope of the problems that are out there. First of all, it's obvious. IPv4 is still there, so we have all the threats of IPv4 in an IPv6 dual stack. But in addition to that, we multiply it by 2, because everything that we can do with IPv4, we can also do with IPv6. So an awful lot of the vulnerabilities that we see in IPv4, common vulnerabilities, are also there in IPv6. But worse, on top of that, there's a whole host of new complexity, of new features in IPv6, but bring with them their own security risks. And rather than call these worse on the slide, you know noticed I've got my IPv6 marketing hat on, and I've called them new. And some of these have got pluses next to them because they are big. They are not small. So let's have a look at something, first of all, that's better, or that is arguably better for IPv6. And that is scanning is hard in IPv6. In IPv4, scanning a whole subnet is trivial. In IPv6, because there are 18 quintillion addresses in a single subnet, it's extremely hard. I did the calculation on a gigabit Ethernet, that's 500,000 years. That's not to say that you can't find addresses to attack. You can, but at least scanning is difficult. Is it possible to get me some water, please? I should have brought some up with me. Thanks. One thing that does keep people awake at night is the fact that with IPv6 we're using public addresses. RFC 1918 addresses, there are no equivalent in IPv6. So the pure evil that is NAT has been removed. And some people associate NAT with security. The brokenness that it provides stops people getting into the network. With IPv6, thank you, Bob, we have end-to-end connectivity restored. Thanks very much. Should be interesting. Stay. But of course we can use firewalls. I have a friend called Phil. Has anybody met him? He's a NAT believer. And when I was building a house in Scotland, the front door wouldn't open. And Phil said to me, Dave, this is fantastic. Your house is secure. I said, hang on, Phil, I want to get in. He said, well, there's a window up there, and you've got a ladder. You can get in through that window. I said, but Phil, I'd rather go in through the front door. I was really quite puzzled. I said, why can't I use a key and the lock? He said, oh, no. Brokenness is much better. And that's the view of a NAT believer. I've still not persuaded him that fixing the door was a good idea. The enemy of security is complexity. So we're going to look at a number of ways in which IPv6 is much more complicated than IPv4. If you look at the IPv6 header, it's a thing of beauty. It's incredibly simple. It's designed to be like a fast, high-performance car. The complexity, however, has been moved into a series of extendable extension headers that can be chained in an ever-growing linked list of complicated headers. Worse than that, some of these headers have sub-options within them. They're also extendable, and they even have variable length padding, and the security experts along here will already be breaking out in a cold sweat. And of course, attackers can make use of this to carry out a whole host of new style attacks that we don't see in IPv4. And I've given some examples up here. They can break all the rules. If a header should be used once, use it twice. If a header should be at the end of a chain, put something after it. If a header should be used only twice, use it 3 times. So they can break all the rules. And this leads to a number of problems. But not only that, long extension header chains can be used to hide attacks, as we'll see later. That's a great deal of additional complexity. But we also have additional complexity in ICMP. In IPv4, ICMP is trivial. You can block most of it with firewalls. In IPv6, ICMP v6 has become a whole host of additional protocols that are crucial to the operation of IPv6. So you can't simply block them. You have to selectively choose which ones you allow, depending on where you are in the network. So this is something that you need to take into consideration. Worse, some ICMP v6 messages even have to traverse firewalls. And then we have neighbor discovery. Neighbor discovery replaces ARP, but it does so much more. It allows you to configure IPv6 nodes automatically. You turn them on and they just work with stateless address auto-configuration. But there are a whole host of new security issues that come with neighbor discovery. For example, let me give you one example that many of you may have heard of. If you send out one packet, a stateless address auto-configuration packet called a router advertisement, this can configure all of the nodes within your subnet. Automatically, you can change the default gateway and the prefix. You can carry out man-in-the-middle, denial of service attacks with one datagram. And if you've got an IPv4 network, you're smiling, but you shouldn't be, because this can happen on your IPv4 network just as easily as on your IPv6 network. You can also attack networks remotely with neighbor discovery protocol. So the equivalent to ARP in IPv6 is neighbor discovery, but it's slightly different from ARP. And because each subnet has got 18 quintillion addresses, which is a lot, an attacker, if it knows your subnet prefix, can send messages to many, many random addresses, and that consumes resources within your router. And this has the potential to do a denial of service on that router and to interrupt communications that's going through that router. This is not good. Transition mechanisms. There was a time when in the IETF, and Tim will confirm this, that to gain fame and glory, you invented a new transition mechanism. And so today we have over 30 of these truly horrible things that were intended to help us move from IPv4 to IPv6. They're all bad. And the reason they're bad is they couple together IPv4 and IPv6. You can see the attackers rubbing their hands with glee as they think of the opportunities for laundering attacks from IPv4 to IPv6, making forensics and tracing back to the source almost impossible. Not only that, but many of these transition mechanisms are built into the stacks and they come as standard. In some, they're turned on by default. So you need to be very aware of transition mechanisms, and I haven't got time to even touch upon the security issues within those. Then we have the problem of address reputation. Anybody here manage mail servers? Right. So you use reverse DNS block lists, right? To check the reputation of IP addresses for SMTP, anti-spam, along maybe with SPF or DKIM. Well, with IPv6, the problem that you have is that there are so many addresses that it's very difficult to record their reputation. With IPv4, it's trivial. 4 billion addresses, any of us can record that. But with IPv6, 18 quintillion /64 subnets is a very big number. Now, it's not as bad as I've shown on this slide, because the number that's actually out there of allocated prefixes is tiny compared to this, but it's still ginormous compared to IPv4. So you were forced instead to look at the reputation of prefixes. And then you have the problem that you might have multiple tenants within, say, a /48, or in some cloud providers, multiple tenants within a /64. This is like you being treated by the police as though you were your neighbour who's a thief. Or maybe where I live, that's true. Not only that, but solutions to get around this problem by some large providers that I won't name can lead to further problems. So, for example, let's make up one. Office 377 might provide an SMTP service. And for IPv6, Office 377, rather than using address reputation, SPF and DKIM and weighting them, it says you have to. The sender has to have SPF or DKIM over IPv6, or we will reject the mail. So what you end up with is two worlds. A world where if you send mail, legitimate mail over IPv4, it arrives, no problem. If you send legitimate mail over IPv6, it's dropped. This is not a marketing poster for IPv6. So sometimes the solutions are worse than the problem. It also has a huge impact, and we don't have time to talk about this, on analytics, governance, legal intercept, and forensics, because the size of the address space is enormous. Okay, let's have a look at some of the solutions. Some of you may have heard in the past of how great IPv6 is because it has IPSec. Well, IPv4's got IPSec. This is not, and they're the same. So this is not a great story. However, there is a subtle difference. And the subtle difference is this. In IPv4, we commonly use IPSec in tunnel mode, not in transport mode. Why? Oh, it's on the slide. Useless question. Because of NAT. And so we terminate our IPSec tunnels, our VPNs, on our edge VPN concentrators. With IPv6, we have global addresses everywhere and no NAT. So we can use transport mode IPSec and we can terminate that wherever we please. So we have clients, for example, that have moved to Microsoft Direct Access, which uses this, and deployed IPv6 for this very reason, so they can get rid of their VPN concentrators. We also have other clients where they have actually used transport mode IPSec in their data centers for all traffic. I'm not suggesting that doesn't have its problems. IPv6 originally used addresses that were based on your MAC address, EUI64 addresses, well, modified EUI64 addresses. This gives away information that can be valuable to attackers when you connect and travel over the internet. So today there are two addresses in IPv6, it's considered best practice to use, and they are, first of all, the opaque static address, which is a randomly generated address that doesn't change, that you use if you're providing services over that address. And also another address called privacy addresses. And these are where you have a temporary additional address that you throw away every few hours or every day. And this is the address that your client applications use for connecting out onto the global internet to sites that you may not trust, where you're worried about the address being harvested and used for future attacks. But because you throw it away every day, this is not a problem. Of course, it is a management overhead, because you now have a huge number of changing addresses that you need to track for your audit or good governance purposes. So privacy addresses are not without their problems. Anybody know what opaque static addresses are called in Windows? No. I'll tell you, privacy addresses. Privacy addresses in Windows are called temporary addresses. Yes, Tim. Yeah. That's just to confuse us. Anybody here using secure neighbour discovery? I'm guessing not. This is a solution to the problem of how do you secure neighbour discovery. The problem is it's not widely implemented, except for maybe on switches and routers. So you are very unlikely to be using it. So how then do we secure our lands against some of the attacks that I mentioned earlier? Well, the good news is there are a set of techniques that have been invented that can help us. These include neighbour discovery inspection or equivalents to that, router advertisement guard, where it checks the router advertisements to make sure that they come from legitimate routers, and there are a number of ways that can be done. And if they're not legitimate, they're dropped and logged. DHCP-v6 Shield, which is similar to DHCP snooping in IPv4, and MLD snooping, which is designed to improve multicast, which is big in IPv6, performance, but can also be used to mitigate some multicast attacks. Now, these all look great, and you're strongly advised to include these in your infrastructure. However, all of them can be circumvented. And they can be circumvented easily through the use of extension headers. And the reason for that is switches look for router advertisements or the other messages in particular places in the packet. They do it in hardware, so that it's done very, very quickly. But if you add in some additional unnecessary extension headers, you can push the position, making it difficult to traverse that train and reach the attack and detect it. Even worse, you could even push the attack into a fragment so that your switches or your intrusion detection devices would actually have to track fragments as well. So this is a problem. The good news is that there are recent standards and operational best practice that can help you mitigate this. Whilst it's difficult to mitigate in your switches and in your Layer 2 environment, you can mitigate it on the end nodes. So that was a whistle-stop tour of IPv6 security. What about the future? Where do I think things are going? Well, we already have clients that are deploying IPv6 only networks, which is why I was interested in how David was getting on with that. And you may well have heard of people like Microsoft and Cisco, the fact that Facebook and LinkedIn have got IPv6 only networks. So this is the way to go. And the reason it's the way to go is that once you deploy IPv6, you don't want to continue to have to manage IPv4. IPv6 gives you everything you need. It does it better. IPv4 is now just an overhead, a cost, a complexity. From a security perspective, you also want to get rid of IPv4, because in so doing, you get rid of all of the IPv4 vulnerabilities, plus, oh joy, you get rid of the vulnerabilities related to transition mechanisms too. So I see in the future, the best way to go is to deploy IPv6 only. Thank you very much. And And that's it. And I did do it. My 50-minute talk, I fitted into 25 minutes. Are there any questions? Thank you very much. I get the smiley's face.
Thank you, David. Do we have any questions?
Thanks. So what is holding people back from adopting IPv6? My understanding is that there are costs involved and not all of the infrastructure is IPv6 ready, but perhaps you could explain it better.
Well, really, I'm sorry I didn't catch your name.
James Crawshaw from Heavy Reading.
Hi, James. Well, I'm not the best person to ask because I don't understand why people are holding back. Yeah, it's a mystery to me, James. From my perspective, this is a difficult one. But you're right. There is a big perception that there is additional costs with IPv6. But in actual fact, it's not as bad as people tend to think. And there are a number of reasons for that. One is they're looking at it from the wrong angle. And they're looking at it, this is a great cost, a massive project that we need to do to deploy IPv6. And they're forgetting that they're actually in a position where most of their infrastructure is already IPv6 enabled. Right? They're also forgetting that there are certain things that they should be doing regardless of whether they deploy or not. And security is the big example. So they need, from a business perspective, to secure their networks, and they should be securing them against IPv6. That should not be judged as a cost against deploying IPv6. So my view is they tend to overestimate what should be allocated against IPv6 deployment, even though it can be a big project in some organisations and very expensive. There's an awful lot of items in there that are not actually things you should budget against IPv6. And I don't really want to go hunting for all the other problems. For most organisations, there is no reason today. For small enterprises, it's trivial. They can get it from their upstream provider. Their platforms will be IPv6 capable now. The biggest problem that most people face is actually staff training and awareness. Does everybody agree with me?
Okay, another question over there.
Tim Robinson of TXRX Communications. Just as an observation, I do a lot of sort of IT and internet-y stuff for small businesses, some of which want to have multiple providers, say a BT Internet and a Sky Broadband, and to deploy IPv6 with that is very difficult because they each have their own separate address space.
That is a very important point. There is a subset of people out there who are doing something that in IPv4 is trivial. One of the side effects of using the pure evil that is NAT is that we have gained a benefit. And that benefit is you have RFC 1918 addresses, you can have multiple providers, and through NAT, it is trivial to do multi-homing. For the big enterprises, or even small ones that are using PI space, this is not a problem, right? For the small users and end users, it's also not a problem. So there's a whole world out there for which this is not a problem. But there's a particular subset of organisations where this is a problem. Now, the IETF has done a massive amount of work on this, and there have been a number of proposals for solutions, some of which may well come to pass in the near future. But it has been a thorn in the side of IPv6 deployments, I agree with you. And the solution is not IPv6 NAT. Max.
Hi, Max from the RIPE NCC. There's been work done in this field, like connecting multiple ISPs with IPv6, and you can check mostly the work done by Jen Linkova, and you can check RFC 8475. That mentions how to do multi-homing with IPv6 using addresses from different providers. So that's it's been worked on.
Yeah. Thank you, Max.
Thank you.
Okay, thank you very much, David.
Thank you.